So thanks a lot. It's also, like Ramesh, it's my first time in Croatia. It's really beautiful here, and I'm particularly impressed by the fact that this is the 35th year of this conference. This is fairly unique, I think, for our field where there's this kind of continuity. So I am, in fact, from George Mason. Where is Mason? Well, it's basically Washington, D.C. If you've ever flown into Dulles Airport, you were about 8 miles away from there. Mason, unlike other places in the United States, is part of the University of Virginia system. But because we're Virginia, we name our universities after famous people, except for the University of Virginia. So I'm going to talk about this thing called the Internet of Things, which is currently really big hype. It's known by a bunch of different terminologies, and I also note that there are some papers later in this conference that are going to talk about Internet of Things, so you get some more actual technical detail. It means a lot of things to a lot of different people, but I think it's sort of interesting because so Ramesh was talking about, you know, old wine in new bottles. I actually think that there's some stuff here that actually is different and unique from a computer science perspective. And I think that that's going to impact a lot of what the rest of us and you all do, especially, you know, folks who do things like analytics. So my bias is systems, it is networking, and so it's going to have a strong flavor of that, but take that for essentially for what it's worth. So what is the Internet of Things? Well, probably the best way to understand it is sort of more of a functional view. It's really a convergence of multiple types of technologies. Certainly networking, and in particular wireless at the edge networking. So that's an important part. Wireless networking has been around for a long time. When I say wireless networking, I'm including everything. Bluetooth, but also 802.15.4, which is the basis of what's known as Zigbee networking, Wi-Fi, WiMAX, all of that sort of stuff. But what's happening is that there are other things, there are other kinds of technology that are converging in that space as well. So a second type of technology is essentially what we know as embedded systems technology. This is stuff that's sort of embedded into the environment. So it's stuff that's, let's say, built into the infrastructure of a building. And if you're staying at this hotel, you know, you probably have already noticed that in your own room. But it's also stuff that's actually being increasingly added into the physical world. So that's, I would say, the second of the three different tiers. And the third are really sensors and RFID tags. And so we're going to talk about RFID a little bit later. When we talk about sensors, sensors sometimes mean essentially multifunctional nodes. What I mean by sensors are literally sensors, something that actually senses the environment. So it tells you essentially what the temperature is or how much light is being produced. So when you add all of these three things together, then you get this thing called the Internet of Things. So I'm not yet going to tell you what I think the definition is. I want to first motivate it by a bunch of examples. And this is where you can sort to see where a lot of the hype comes from, because at this point, it's come to represent several different application classes. So the first application class, some of you probably heard of this, is essentially what are known as wireless sensor networks. So wireless sensor networks sort of came out of the Smart Dust program from Berkeley in the late 1990s. And the basic idea there was that you would use essentially very small nodes, and you would put them in some place that normally, let's say, was inaccessible. So one of the things they were developed for was things like battlefield management. And they're also used for other things like monitoring wildfires or monitoring volcanoes. And the idea is sort of appealing. The idea is that essentially you somehow deploy these little motes from a helicopter, you drop them on the floor, and then you walk away and you never go back. And then what they do is they wake up and they configure themselves, and they really only have one function in life. Whatever their mission in life is, that's what they do. So it may be the case that they're dropped over a forest and are looking for forest fires. And so they wake up and they diagnose what they need to do, and they basically say, okay, I need to look for a forest fire, but equally important, I need to look for my neighbors. And so each mote basically wakes up and says, okay, here I am, can you talk to me? And so if anyone is in wireless radio range, they basically say, okay, I can talk to you. And then at some point they form essentially a multi-hop ad hoc network, which means that there's no basic infrastructure there. They're monitoring themselves. and they continually look for different events. If they think, let's say that there's a fire, what they need to do is cooperatively decide, you know, just because I think the temperature is 150 degrees doesn't mean that's correct. We need to form some sort of consensus. And then when that happens, what they do is they rapidly exfiltrate some sort of signal out, basically saying, there's a fire, go ahead and do something. And so wireless sensor networks has been around for a long time, and you know, those of you who are in computer science or systems, you know about this. But this is essentially what this has happened is that this area, this application, is sort of folded into one type of an IoT application. But there are others, and the second sort of important application is a smart grid. So the smart grid means that there's some sort of, the power company wants to sort of intelligently deliver power supplies. And in particular, what power companies want to do is they want to essentially do real-time pricing. So if there's a high demand, you pay more. If there's a low demand, they pay less. And they want consumers to be able to actually be in real time, be informed of these decisions. And so what's happening, what smart grid companies are doing, and actually in this, I would imagine that in Europe is somewhat ahead of many of the US companies, is that they're overlaying IoT technologies inside a consumer's home to basically say, this is how you're currently using your energy. This is what you're paying for air conditioning. This is what you're paying for your refrigeration. This is the current situation. If you agree to turn off, these devices, your usage is going to go down. And at the consumer level, what's happening is that these tiny little embedded devices to do power management are essentially becoming part of the Internet of Things. The other thing, which I don't have a slide about, is things like data center management. So as some of you know that in data centers, the major hit is power. You want to really reduce power. You want to reduce the temperature. The way that's done is essentially all of these systems are now overlaid with these very, very small types of devices. So another extremely important application class is SmartX. So you've heard of, there are smart cities, there's smart anything. You can take sort of anything that you want and you add the word smart in front of it, and all of a sudden that becomes an Internet of Things application. But the reality is that there's actually a lot out there. And so I thought there are sort of two applications that I wanted to talk about. And one is this notion of doing essentially smart buildings. And in particular, there's an alliance out there. I don't have any affiliation with them, but they're called the N-Ocean Alliance. And what they've done is that they've set up a bunch of industry standards that essentially say, if you make a really clever device that does some kind of power management and can do energy harvesting, in other words, can actually gather energy from the environment, if you follow these standards, you can interoperate with other sorts of devices. So one sort of neat thing that N-Ocean does is that they have all of these ways of turning on and off lights. And the way that they generate energy is simply from the press of a button. So it doesn't need a battery. It doesn't need electricity. When you press the button, it goes ahead and stores a little bit of energy and, let's say, turns the light on and off. So I don't know how many of you are staying in this hotel here, but sort of that technology is in these rooms. And so if you open up the balcony, what instantly happens? The air conditioner instantly goes off. And so that's an example. I don't know the actual technology that they have here, but that's sort of a very sort of popular IoT type of technology. So you open up the door and instantly the air conditioner goes off. Another interesting application is in the city in Spain. So what they've done, they have a bad parking problem, which is sort of all over the world. And what they've done is under every parking space, they've basically buried a sensor, a wireless sensor. They've stuck a battery in it. And it wirelessly interacts with essentially other sensors around it. It hops, the signal hops until it hits some kind of access point. And then you pull out your app on your smartphone or whatever, and it tells you where the nearest parking space is. And so this is an example of smart cities. So these three different sorts of applications seem sort of different, but there actually are commonalities, and that's where I think this notion of the Internet of Things is certainly becoming important from at least a CS perspective. So let me tell you why this is sort of neat for those of us who are sort of networking and CS geeks. In a traditional scenario for embedded systems, whatever the embedded systems are, the embedded wireless systems, any kind of sensor systems or HVAC, what essentially used to always happen, and still to a large part does, is that you have a whole bunch of specialized protocols that are running inside of that system. So you would be able to go out and buy a bunch of control systems from, let's say, Honeywell, and you would install it in your building, and Honeywell is will happily sell you all of this stuff. And the Honeywell devices talk to each other, and they bounce around, and then at some point what happens is that they hit some kind of specialized node or specialized gateway. And that node or gateway does some kind of protocol conversion or does some kind of security or some kind of processing. And then it does something that translates it from the format that, let's say, Honeywell does into some sort of back-end system. So from the perspective of the system, what it looks like is something like the diagram that you see. You can sort of see the smart whatever, and then you hit a specialized gateway, and then the back end is sort of this opaque cloud, and the cloud works however it works. So the distinction between that environment and the Internet of Things is that basically that gateway goes away. And so what it looks like is something like this. All of a sudden now, what's happening is that all of these little devices are now part of the Internet. And so when we say part of the Internet, what do we really actually mean? If we're part of the Internet, what that really means is that we have an IP address. So you all know what IP addresses are, 129 whatever it is. But what does an IP address really give you from a systems point of view? It gives you two things that makes the Internet work and makes IoT so interesting. It gives you global addressability, which means that all that you need to know is the actual IP address, and it gives you global routability. So I might not know where a particular sensor lives in the world, but if it's actually on IP, like an IP web page, if I put an IP packet into the system, I expect that the Internet protocol at some point will bounce my packet until it hits this web server and then bounces way back. And I don't care where it is, I just want the Internet to work. Well, what's happening in the Internet of Things, because that gateway is going away, and because we have IP addressability, we'll more or less get the same sort of thing. So when I go home, I might not care that much really what the temperature is in my room on the 8th floor, or maybe I do. And depending upon how the security is set up and how it's configuration, I can go home, and if I know what the IP address is of that sensor in my room, I can go ahead and basically ping it. So that means that all of a sudden, rather than essentially, a bunch of web servers or human readable things or whatever, we have all of these different machines that are now on the Internet. And so this is where some of the potential hype is going to start to come in. I think there's a lot of interesting hype, which I'm going to talk about. I'm going to talk about some devices, and then I'm going to talk about some of the research challenges. And if you have any, if you have any questions or objections, please, just go ahead and call them out. So why now? Many of you have heard of these laws. In some sense, if you believe in both Moore's law and Bell's law, it's not that surprising. Moore's law still holds and will continue to hold for a long time until I guess we hit some kind of quantum barrier that we can't go beyond that. And then there's also Bell's law, which predicted a while ago that we get a totally new application class roughly every decade. And in fact, the Internet of Things is simply part of that. And so the Internet of Things in some sense is a way of essentially instrumenting the physical world. So now we can stream data from the physical world. IDEA has been around for a long time, but now it's actually starting to become true. So if you look at it from that perspective, it's probably not, it's not surprising actually that it's happening. So I want to spend a little bit of time just talking about some of these devices. So again, wireless sensor networks have been around for a long time. If you haven't really looked at them for a while, or you're not really sure what they are, they're essentially these tiny little packages, and so this is That's a wireless. That's actually a wireless node. A wireless sensor network or a wireless sensor node really consists of three things. It consists of course, physical sensors to be able to see what's going on in the environment. It consists of a CPU. And so the picture I have here is actually of a 16-bit CPU. I actually went to an industrial conference in Chicago a couple of weeks ago where, people are actually manufacturing this stuff. And it actually turns out that the standard now is becoming a 32-bit processor. 32-bit processor is pretty powerful. Okay, you have 64 bits in your laptop. 30-bit processor is pretty powerful. For those of you who care, it's based upon the ARM architecture, so ARM Cortex. 32-bit processors that cost less than $1 mean that you can really get a lot of stuff done. The third component of a wireless sensor network node is a radio transceiver. And so a typical protocol that it runs is something called 802.15.4, which you can think of as sort of like Bluetooth, but even lower power than Bluetooth. So Bluetooth probably consumes an order of magnitude more power than 802.15.4. So you have one of these tiny little motes. It has an ultra low power radio transceiver. It has a bunch of sensors on it. And it has, at this point, a 32-bit processor. So there are a lot of constraints. The constraints are memory. Memory is real expensive. And energy. So if you think about, the thing that rests upon your finger, if you connect two AA batteries to that, the form factor becomes a little bit funky, to say the least. So energy becomes a first-order principle, which is also a way that computing, or at least computer science, is changing. And then even below that, in terms of resources, are RFIDs. And so Ramesh talked a little bit about, the need and importance of essentially understanding RFID data. What's interesting about the RFID space is that RFID tags are getting a little bit smarter. So just to make sure we're on the same page, if I say RFID, what I mean is a device that's energized by the reader. It doesn't have, for the most part, does not carry its own power supply. And its role in life is basically, at least initially, was to basically say, this is my name, and that's it. It has no CPU, although even that's starting to, it still has no CPU, but these things are actually getting smarter and smarter and smarter. So the examples I have here, some of them actually have environmental sensors on them. In fact, one of them is actually, weirdly enough, able to do, in effect, multi-hop networking. So this is a device dumb as a doornail, but can do more than wireless, can actually grab a packet and forward it. So at the bottom, dumb RFID, above that, smart RFID, above that, these wireless motes, and then you just like sort of continuum. It's kind of fluid. It's right. Right. So, motes get, at the top, motes get smarter with 32 bits, but RFID gets smarter, but energy is a constraint. And this is sort of where some of the research becomes sort of interesting. Okay, so I've never actually given an academic talk where I've used a hockey stick marketing prediction. So take it for what it's worth, but there is sort of an interesting point here. So in 2011, we reached the point where the sales of tablets and smartphones permanently, I would argue, surpassed PCs, right? So tablets and smartphones, that trend will never go back. And so as we're teaching introductory computer science classes, we all think probably 5 years from now, no one's going to teach on a laptop. It's all going to be tablets and stuff like that. So think about 10 years ago, if someone told you, I guarantee you that 10 years from now, in your pocket, you're going to have a device that's an order of magnitude roughly more powerful than what's currently on your desktop. And you may or may not have believed it or, whatever. Well, here's the thing about things like the Internet of Things. And again, it's a marketing prediction. Take it for what it's worth, but it might actually happen. In 2020, and this is literally the most conservative estimate I could find. So most of the estimates at the industrial conferences are 100 billion. So this is the most conservative estimate I could find. In 2020, the most conservative estimate I can find is that there will be 16 billion IoT devices connected to the internet. So we have 3 billion PCs and tablets now to 16 billion. Even if that number is off by 50%, that means that the nature of the communication and the data on the internet will start to change. And so another interesting aspect of that communication is the type of communication. So we've been talking a little bit during this conference yesterday, and Ramesh talked a little bit about it today, about, why do we mine Twitter traffic? We mine it because it's an interesting data stream and it's there. Well, what will happen in the Internet of Things is that humans will get out of the loop. And what I mean humans will get out of the loop is that the ultimate consumer of this communication will not be someone sitting behind their smartphone, but will be one machine talking to another machine, and humans won't care. And so this is also a relatively conservative prediction. Again, take it for what it's worth, but so this prediction says in 2016, per month there will be 508 machine-to-machine petabyte communication a month. So an example of some of the things that exist now is I was at this conference and we were talking about smart buildings, and this company from N-Ocean was explaining how they do all of this energy harvesting. And the energy harvesting comes from someone pressing a button. And so what happens is that they install it in a lot of interior spaces like conference rooms or universities. And the way that they harvest energy is from ambient light. And so what happens when people go on vacation? It runs out of energy. And so what happens at that point? Well, the thing can't go totally dead. What happens is that the system notices that it's run out of energy. So what it will periodically do, all of a sudden, is simply turn on the lights in a facility, harvest some more energy, and go away. And so I sort of like this image of these buildings, in some sense, getting life of their own. Well, all of a sudden, the lights go on, the air conditioning goes off. You have no idea why, and then it continues. In terms of data analytics and the predictive stuff, and you folks who do the really smart stuff with data, at some point this might be coming down the pike. I don't know what you'll do with it, but you'll figure out what are you going to do with it, Boris?
Machine-to-machine communication, but typical amount of bits is not big. Right?
Typical amount of bits is quite small, right?
Because there's so many machines.
Because there's so many of them, and partially because there's so many of them, partially because they're more or less always talking to each other. So even if I'm only sending out, if I'm sending out 10 bits every 2 minutes, but there are 20 billion of me, that's a lot of stuff. That's a lot of stuff. In terms of so the question is, I think you're saying, what's the interconnection of the human brain in terms of the actual interconnection size?
Yeah, and how is this going to, impact? Things are going to be going on outside of what we have in control of, that aren't going to be probably nice for us.
Right. Well. Yeah, well, it's a Terminator. I know people. I don't really know. I haven't really thought much about those issues, but there certainly is. People talk about things like swarm intelligence, which has been around in AI for a long, long time. No one's building, swarm intelligence into this stuff, but this is a phenomenal amount of communication. If anything close to this happens, it will dwarf the current internet communication. So stuff will change in ways that obviously we can't predict. Okay, so let me sort of talk about some of the research challenges, and I'm going to talk about it sort of little bit geared towards what I've been doing. Clearly, a lot of people are doing this, and so it's sort of impossible to list the related work because in systems, at least, so many people work on so many different challenges. So let me tell you what some of the research challenges are, and sort of I'll conclude with where sort of what I think is some of the cutting edge stuff. So there are actually a lot of direct contradictions in doing research in this area, which makes it great for academics when we do research. So for this really to work, if you think about the actual internet now, it's basically plug and play. You plug something in and it works. And we know all the different protocol stacks, and that's all great, it works. So for this really for the IoT to really take off, we need, among other things, a communication stack that's highly reliable. And so what does that mean? Well, if you're a networking geek, you know that the IP model is called best effort, which means that it's not reliable. But the reality is that these applications work because they assume some level of reliability. In particular, it's either going to succeed or it's going to fail in a way that it tells you it's going to fail. So IoT requires that. It also needs some sort of internet-enabled communication stack. And that seems that seems completely obvious, but we're going to see in a sec, maybe that's some problems. And it also needs at least some illusion of privacy, security, and human control. And so privacy and security, you know, is a big issue. We've talked about it. It's actually come up in several different discussions here. So, you know, what can we say? What can we say about security and privacy? I don't want to talk a lot about privacy, but let me at least talk a little bit about security. So just from a technical perspective, forgetting about a policy perspective, from a technical perspective, a lot of the way that we get privacy and security and authentication is through cryptography. What we do is we basically set up some kind of a session where we have some kind of cryptographic key, public key, symmetric key, whatever it is. Pick your favorite algorithm, et cetera, et cetera. So what's going to happen now in the Internet of Things is that these devices, for virtually their entire life, will be unattended, which means that I can walk up to it, pull it off the wall, pull it out of a forest, easily, if I'm good at hardware, which I personally am not, but a lot of people are, extract the cryptographic key, and then the game is over. So stealing, you know, someone's smartphone is one thing. You know, you pound through the pin, and that's not too difficult to do. But now if your house essentially now all of a sudden has 1,000 devices, and that's probably not an exaggeration, each of which has a cryptographic key, tracking those keys has become a lot more difficult. So take privacy, take that issue for, you know, whatever you think about it is fine. Whatever part of the spectrum you're on in terms of privacy is fine. But security becomes a lot more difficult. It's an ongoing problem, and there'll be people with graduating PhD students on security in this until way beyond when I retire. So just to understand this is a big issue, and I'm just sort of waving my hands on this one. Okay, so actually what I do want to talk a little bit about is the IP protocol stack. So if you're a networking geek, you sort of know exactly what this is. And if you're not, understand that the way that we build distributed systems that run on the internet, or really any kind of communication protocol, is we do what's called a layered approach. And that means that we have, at the top, we have an application layer, and all that it cares about is talking to other application layers. And below that, we have what's called the transport layer, which does things like end-to-end reliability. And we have something called the network layer, which does things like IP as part of the network layer. And then at the very bottom, what we have is something called the data link layer. And what the data link layer is essentially is concerned with how we do things like wireless transmission. So Wi-Fi is an example of the data link layer. Bluetooth is an example of the data link layer. And so what happens is that every layer just basically plops its data inside of the layer below it and assumes that that part will work perfectly. So when you write your web browser or your brilliant, analytical engine, you don't care about the system because it will work nicely. It will jump through all of these different hoops. And so the reason why the internet has continued to take off is because if you give me a new device and you tell me that, hey, it works on IP, that's great. I don't need to change my application because it's still using IP. And the fact that the technology has changed doesn't actually impact the way I write my application. So perhaps not too surprisingly, given some of the device constraints that are in IoT technology, this assumption is maybe not so correct. So here's one example, and this is sort of work with some of my graduate students. So one of the things that we're sort of interested in doing is essentially doing something called routing on geo-located addresses. And so to geek out a little bit, there are several flavors of IP. The flavor of IP that runs on the Internet of Things is a version called IP version 6. IP version 6 has 128 bits in it. 128 bits means that the size of the address space is 2 to the 128th, which of course is more than the number of elementary particles in the universe. So that makes things sort of neat. So one of the things that you can do in IPv6 is actually make as part of your IP address where the device actually exists in a geographical coordinates. So one of the things that we're working on, and other researchers as well, are essentially embedding things like the geographical coordinate in some node's IP address. And we're also interested in other things like, what happens if you have a mobile IoT application, like you walk into a building which does HVAC, but there's a fire, and you give the fire person some sort of device, and the fire person walks around, and the routing tables therefore change, and you want basically all these updates to happen. In any event, that's actually not the point of this slide. The point of this slide was we spent, when I say we, I mean the graduate students, of course, spent a lot of time banging on some of these applications, and what we used essentially the default academic operating system that works on IoT devices, which is an outstanding system, and I'm not trashing it at all because we know what it's like to do open source, but this is the standard. And so when you download this system, you are basically told that this runs a compliant IoT IP stack. And people, not just academics, but people actually build products on this system because it's actually out there. And so as we developed the system, what we started to see was that performance was terrible. So if you look at the blue line, the y-axis is something called PDR, which stands for packet delivery rate. It's the percentage of packets that actually get through. And the x-axis is how fast we're sending out the packets. So the more packets we send out, the fewer packets we might get because there are collisions and all this kind of stuff. And so we built all these different applications, and what we expected was essentially the blue line. And what we kept getting was the red line. And so it's difficult to read, but as you can, just by eyeballing it, you see that there's a pretty big gap between the blue line and the red line. And we were miserable. And if you've ever developed sort of a prototype experimental system, you know that debugging these things is really horrible. So as a good professor, I basically said, work harder, and then I went home. And as the weeks went on, the answer actually came back. And so let me show you actually what was going on here. Yeah.
So when you say packets delivered, I mean, all the packets do get delivered, but over many attempts.
Well, actually, in this model, there often is not retransmission, so it's not actually TCP. So sometimes if the packets don't go through, but that can actually often be okay. So for instance, if you're reporting the temperature, you don't need 100% reliability.
Okay.
Yeah.
What is the meaning of fragmentation cost?
Yeah, I probably should have avoided this. Let me explain this by going to the next slide. So just for purposes of the talk, assume that we expected the blue line, but what we got was the red line. So this is actually what was happening. When you transmit a packet from any sort of device, the way that it works inside of a system, and if you know about networks, you know all about this, is that there's some sort of user message, and inside of the device, in your laptop, your tablet, your IoT device, essentially it sets up a bunch of different data structures to represent those layers, those network layers. And so again, this is certainly a simplification, so don't yell at me for simplifying it, because I am in fact simplifying it. But what would typically happen in that you take a user message like a web page or temperature, and you send it down to something that may be running the internet protocol and then to the data link protocol. So in this example here, the green is the user message. The red represents the empty data structure that's waiting for the user message but has some other metadata associated with it. And the blue structure has an even larger empty data structure that's representing waiting for more stuff. And so in a perfect scenario, what happens is that the green is stuck inside of the red, the green and the red are stuck inside of the blue, and bang, you send the packet out, it goes down the wireless link, and the other side gets it, and everyone's happy. And you have 100% packet delivery ratio. So that's all good. And when you take networking 101, this is essentially what you learn. So in IP, what happens is that sometimes the data link layer may not be large enough to actually accept larger messages. And so Wi-Fi can accept a big message, but Bluetooth maybe not so much, and 802.15.4 maybe not so much. So IP says, no problem. What I'm going to do is I'm going to fragment that packet. I'm going to chop it up into little bits. And so in that example here, what happens is that if the data link frame is not large enough to hold the entire message, no big deal. We set up 3 different frames, and we basically say, okay, I'm going to do packet fragmentation. Rather than sending out 1 data link frame, I send out 3 data link frames, and they all get there, and these 3 data link frames correspond to 1 user message, and so on. Now, once again, I have 100% packet delivery. No big deal. It's worked for a long, long time. In fact, IP, has been smarter than that. So what happens in this scenario here, if 1 user message, what happens in a wireless link, which is sort of common, if one of these things gets all gorked up, it gets dropped. So all of a sudden, you don't have the user message. So what do? You normally don't, give up and go home. You simply retransmit the packet. What happens at the other end, Wi-Fi does this perfectly, is that the other end simply reassembles it, and boom, once again, you have the perfect green message, and everything is good. And so, of course, the punchline here, which you probably guessed at this point, is that the standard operating system that we're building all these academic projects and some commercial products, which I won't mention what they are in effect not doing this correctly. So what's happening is that the operating system is actually not, because it's not totally IP compliant, it's difficult to say it's not IP compliant. While it turned out it was doing the retransmission, this fragment that's showing up late, the thing at the other side was saying, no go, I don't know what this is, so the entire message is lost. So what happened was, I'm not going to go back to that graph there, but we're getting this red line because what we were using along with everyone else was essentially basically saying, if this happens, something really bad is going on, the message did not get through, and so the packet was lost. Not that this example is profound or earth-shaking. What it does show, though, is that the things that when we, building systems, things that used to always work right out of the box don't necessarily actually work. And it can be very difficult and painful to debug. Again, why? Because, unlike a tablet which may have a gigabytes of RAM, an average IoT device might have about 4K worth of flash and 1K worth of RAM. So when was the last time you taught a student to program something if they had 1K of RAM? Even a 32-bit processor is not going to help you. Okay, so let me sort of wrap up here with what I think are sort of some of the interesting cutting-edge issues, partially because this is what I'm working on. So again, take it for what it's worth. I think ultimately what we would like to push these systems on is to essentially get them to do something that actually involves a mission-critical application. So mission-critical applications can be things like avionics, can be in a car, can be some kind of industrial control. It seems that the ultimate solution to this where this technology is going to be enable these other things that are important, health, medical stuff. So the problem here is that what you want to do is you want to minimize energy consumption, but you want to do you want to get some sort of performance-sensitive application. That immediately induces a really nasty cycle. And here's the cycle. The cycle is that if you have a high processing communication rate, if you want a real-time system, what you get, of course, is better performance. This is how real-time systems work. Avionics, cars, et cetera, et cetera. Of course, the problem is once you do this, you get high energy consumption and you get very short or disrupted system lifetime. And so the problem is, can we start to engineer systems that can perform real-time, mission-critical tasks that do energy harvesting? And so we're working on this, and in fact, I'm working on Hakan. Aiden is my colleague, and these are some of my PhD students. So let me just talk a little bit about some of the results that we're getting. What can we be done? Well, one thing that we can actually do is look at maybe new hardware techniques And again, not geeking out too much, CPUs do what's called dynamic voltage for frequency scaling, which means that they can slow down. If they slow down, you use less juice. Turns out that radios can do something similar. That's called dynamic modulation scaling. It's a way of essentially changing the energy per symbol to get more bits or fewer bits. So it turns out that there may be ways of combining both DVS and DMS to actually get hard real-time systems. Another thing that we can actually do is basically better understand some of the IoT requirements. So let me just give you a couple of quick results, and then we can go to the next session. So sorry for a little bit of math here. One thing that we managed to do is we've modeled these systems as what's known as a hard real-time system. In computer science, a hard real-time system means that it's a deadline. All that we care about is time, the time to complete something. And so if you add both DVS and DMS, the exact format of this equation don't really matter too much, but the tuning knobs are the frequency of the CPU and the modulation rate of the radio. So you can play with those tuning knobs and you can get different types of performance. If you model it this way and you add some sort of energy harvesting, when I say energy harvesting, I mean if you can build some kind of prediction device to tell you actually how much harvesting you can get, you can actually come up with some pretty good ways of getting some sort of sustained real-time performance. So I'm not going to do a drill down into what these graphs mean. So not surprisingly, higher is better. So my stuff is high, is at the top, and the sort of the off-the-shelf stuff is at the bottom. But at least for some of these systems that do some sort of predictive energy harvesting, we did in fact demonstrate that we can get sustained predictable real-time performance. So another approach is essentially basically being starting from the application point of view and understanding actually what good system performance is. So it used to be the case when people do computer systems research, more is always thought to be better. So if you have twice the throughput that I have, you're twice as good as I am. That's not always true. So we use an idea called network utility maximization, where we basically said the utility that the system gets is actually a concave function of the sensing that it's actually doing. If you make that assumption, which is probably sort of reasonable, we showed that this could be cast as an optimization problem, and we proved the existence of an optimal control algorithm. And so for this sort of system, it actually works pretty well, and we won a best paper award at an ACM conference. And so what we're currently working on are this geolocation stuff that we'll be talking about. We're going to keep pushing this hard real-time model to make the workload model a little bit more flexible. And we're going to start to look at techniques called network coding, which has nothing to do with computer coding. Network coding is a way of essentially representing the data in a certain way where you can get a high level of reliability. And so a lot of research challenges here, but the takeaway is maybe not the research challenges. The takeaway is that this thing is probably coming. This thing is coming. Believe as much as the hype as you want, but at some point it really will impact traffic on the internet, especially machine-to-machine communication. So I think